Hello, chemists. In this video, we've got writing complete ionic equations. So from this video, you will learn what a complete ionic equation is and how it differs from a normal chemical equation that you're used to seeing at this point. And you will learn how and when to break apart formulas into ions. You will know you're successful when you can write a complete ionic equation when given the chemical equation. So what is actually happening in these aqueous solutions? That's what we have to understand to really dig into these ionic equations we're going to be looking at. So I've given you sodium chloride here. This is normal table salt, and we're putting it into some water. So this is what it looks like as a solid. You shake it out of the salt shaker, and this is the molecule that you have. You've got the chloride ions in green, the little sodium ions in pink, and they are all together in what we call a crystal. That's uh, not really something you have to know for this, but the fact is that they are all together. Now, ionic means that they are held together with that positive and negative charge because we have a cation and an anion. We've got that transfer of electrons so that the shells are happy. That creates the charges, and then they are held together by opposite charges. These are all things we discussed last semester. Now it's important because when we start putting them into water, so we've gone from A into B, this big molecule starts to break apart because those water molecules are also positive and negative, and they are pulling apart what was the sodium chloride molecule. So it starts breaking down until it gets down to the ions that we are using to write that formula. The sodium has a +1 charge, that is the sodium ion. The chlorine would have a -1 charge, but these things have now been pulled apart. It's still sodium chloride because when you take this water back out, you dehydrate it or you let the water evaporate, it'll come back to this crystal state. All of those ions will come closer together again because of that plus and minus opposite charges. But in an aqueous solution, which is just a fancy way to say in water, water also has those same charges. So it's going to disperse them. And this is called dissociation. Not to be confused with dissolving. That is actually a different thing, and we'll talk about it later in class. But dissociation, or the molecule dissociates. So what does this look like writing these chemical formulas into ions? Let's take a look at them here. So we've got a list of formulas here, and essentially you're doing kind of a reverse crisscross from when you normally write these formulas. You go and find the charge on the ion, usually from the periodic table, or it's given to you somehow, and you crisscross the charge to write the formula. We're going a little bit backwards this time. So sodium chloride, like we've been discussing, now turns into sodium ion and chloride ion. It's got a +1 charge, a -1 charge. It is so important that you write these charges and the plus or minus sign. It's got to be positive or negative, and it's got to have a number. If they don't have this, it's assumed to be a neutral atom, and that is a totally different thing. So you have got to include all of these charges when writing ionic formulas. If we've got something like magnesium oxide, there's no numbers here, but if we did the crisscross, it would be 2, and that would simplify down. So when we uncrisscross them, we go ahead and write those 2's again, because now we have 2 separate entities, 2 separate ions, magnesium ion and oxide ion. Do the same thing with this aluminum sulfide. Aluminum's a +3, sulfur's a -2. Copper and nitrogen. Now here we've got a transition metal, and so sometimes we don't know exactly what the charge on these are. If we're writing the name out, these are the ones we put in the Roman numerals. So we actually have to look at the other side of this to see what that charge would be. So that's where this 2 is coming from. Copper is not always 2, as we'll see in this next one. This one is copper 3. So you've really got to pay attention to that uncrisscross method, if you will. So these were just singular elements that have been put together, copper and bromine, copper and nitrogen. What if we have polyatomic ions? Well, you keep these as one unit. So lithium nitrate becomes lithium ion and the nitrate ion. This all stays together. You don't try to break up the nitrogen and the oxygen. It's all one polyatomic ion, a multi-atomed ion. Same here, iron and sulfate. Again, we got the +2 for iron from the fact that sulfate is a -2, and there are just one of each. It's been simplified, so we can figure out that transition metal. And this one actually has 2 polyatomic ions with it. The ammonium ion is one of the few cations in the polyatomic world. And then we have cyanide ion. Looking at these in an equation, these are all going to be double replacement reactions. So that's very important that we look at that. We're going to have 2 compounds on each side of the arrow. The trick here is anything with this AQ that's been given to you, that means aqueous, those are the ones you break apart. If it's a solid like this, if it's a liquid, if it's a gas, if it's anything other than AQ, you leave the whole thing together. Only the aqueous ones are broken apart. So we've got our sodium and bromine here. We've got sodium and bromide ion broken into the sodium ion, the bromide ion. Again, we've got hydrogen and chlorine. There's our hydrogen ion, our chloride ion, our hydrogen and bromine over here. And here, this NaCl is a solid. It was not broken down. So if it is indicated that it's a solid, a liquid or a gas, anything other than AQ, do not break it apart. So go ahead and try this one out. Pause the video, see what you can do with it. Okay, here is the complete ionic equation for this one. Again, we've got the polyatomic ions that are sticking together as one unit. Those transition metals, you really got to look at that uncrisscross to get the correct ionic charge here. I cannot stress this enough. Make sure you write all of these charges. I know it gets tedious. I know this is really long, but that's how it's done. Otherwise, it's just a regular sodium atom. It's not a sodium ion. There is a huge difference in the chemistry world. And again, here, this lead to iodide is a solid, so it does not get broken apart. It did not change. So here are your practice problems for writing complete ionic reactions. Go ahead and check these out. I'll give you the answers here in a moment. Okay, here are your answers from your practice problems. Again, make sure you write the charges out fully. Positive and negative signs, numbers, everything. As always, you can send me any questions using that teacher information and links folder, but now hopefully you're more confident in writing your complete ionic equations.